Okay. Well, we still have 44 people in the class, but under 50 people here, so I guess a lot of your classmates feel like they're the Wicked Witch of the West and will melt in the rain. Hopefully they'll at least watch the video, and hopefully the video will actually be made. So today I'll be closing out chapter 1. And then next week when we start getting the next chapter, that's where we'll actually learn specific techniques for solving differential equations. But today will be about the part that comes before you are tasked with solving a differential equation, and that is coming up with a differential equation in the first place from some kind of real-world application. And from a verbal description of that application, how does the differential equation come about that will then be solved. So, as an example, Newton's second law, which is, I know we have at least one physics major in the class. Yeah, so force is equal to mass times acceleration. Physical laws like this play a large role in deriving differential equations from some non-mathematical description of a problem. And how we can see that is by keeping in mind what acceleration is. How can I write acceleration as a derivative of something? There's more than one right answer. Yeah, so we'll stick with first order equations today. So mass times the derivative of velocity with respect to time. What's another?
Position.
Second derivative of position. Since velocity is a derivative of position, acceleration would be the second derivative. I'll use p for position with respect to time. Okay. Now, right, so going back to an example I talked about before, a falling object. So we need to keep to account the forces that are acting on the object. What will be one force that is acting on a falling object?
Gravity.
The gravity is the most obvious one. So that's going to contribute g to the acceleration. Now, can anyone name another one?
Air resistance.
Sorry?
Air resistance.
Yeah, air resistance. Who knows another term for air resistance?
Drag.
Drag, yes. Okay. Okay. So with drag, how can we express that? So again, based on physical laws or observations, the contribution of with gravity being one force, so the contribution of a force stemming from drag will be proportional to the velocity. I need to put a constant of proportionality here, so I'm going to call that constant gamma and include a minus sign. Now, before I go any further, I need to talk about how I can justify making gravity positive and this force due to drag negative. So because certainly air resistance is something that is going to inhibit falling. It's going to reduce that velocity in the direction of motion. Now, I need to decide on an orientation. Like so based on direction of motion, I can choose to make downward direction positive. And in that case, these signs, having gravity positive and the drag negative, makes sense. If downward is assigned a positive orientation. Or I go the other way, since the object is going down, and think of it as height or position being going negative, decreasing, then I should switch the signs. Okay, so if so going down is given a positive orientation. That means that the force, the total force coming from both of these, is going to be G minus gamma V. But then, by Newton's second law, I'm just going to equate that to the other side, mass times acceleration. So my differential equation is going to be mass times derivative of velocity is equal to G minus gamma V. So we have a first order differential equation for modeling velocity, and then I can go ahead and solve that. In fact, based on what was seen in class on Monday, we can solve this equation. It's of the same form. If I divide both sides by the constant m, then because we looked at differential equations last time of a form like dy dt is equal to ay minus b, so constant times your unknown, plus or minus another constant, and that's exactly what we have here. Okay. Once you have a differential equation, from the problem data, you would also have to formulate initial conditions. So V of 0, the initial condition would be whatever is known to be the initial velocity of a falling object, and then you can proceed from there and get a unique solution. So this is one example of how physical laws can be used to obtain a differential equation. Questions? The homework for this section is all about statement of differential equations rather than solving them. Now, all right. So more examples. Well, I'll label this my first one. Another one that's very closely related, also coming from Newton. Newton's law of cooling. Although I should point out, I will give a disclaimer, but I absolutely do not know the history in this case. But we come across all kinds of things that are named after certain famous scientists like Newton, or mathematics, Gauss or Euler, etc. Or other fields, Heisenberg, uncertainty principle. But the naming is not always necessarily accurate. To give an example from my community, if any of you have taken linear algebra, one of the things you learn there is Gaussian elimination for solving systems of linear equations. So you think, Carl Friedrich Gauss must have invented Gaussian elimination. And no, he absolutely did not. He had absolutely nothing to do with it. He lived a few centuries ago, and Gaussian elimination has been known from thousands of years ago in China. So, and they can be complicated by the fact that, for instance, my own advisor, Gene Golub at Stanford, who was the foremost researcher in the world, in my opinion anyway, in numerical linear algebra, refused to have one of his own algorithms named after him. So once he passed away, then his friends changed that, and now it is named after him. So, something to think about when you see things named after people. I've not allowed my own algorithms to be named after me either. Okay, so Newton's law of cooling. If capital T refers to the temperature, and lowercase t, of course, refers to time, so Newton's law of cooling states that the change in temperature with respect to time is proportional to the difference between that temperature and T sub m, which I use to refer to the surrounding temperature, the ambient temperature. So what will happen is, it means that as time goes to infinity, if there's no additional heat source or cooling source to change the temperature, eventually the temperature throughout the environment setting will converge to whatever that ambient temperature is. Okay, so then whatever the temperature is currently, that would serve as the initial value for your initial. Now, if we compare this kind of differential equation, just formula-wise, to the first one, technically they're both of the same form, that you have your time derivative is equal to some constant times your dependent variable, and then there's some other term that is also a constant. So even though we have differential equations that come from very different application areas, using completely different information, everything is a completely different meaning, often the solution techniques will be exactly the same, especially when it comes to first order equations. When we solve first order equations, we're going to learn about certain subtypes, equations that are separable, that are linear, and exact, etc. And we'll have solution methods for each one. Well, really, as we'll see, they're all kind of the same thing. So the mathematical techniques have a wide variety of uses across application areas. Which is why it's important that people from different fields, such as physics and polymer science, etc., have at least some working knowledge of them. Okay. Another example, population growth. Okay. So if P refers to population, then we could model population growth using equations such as this. Constant R times the population minus the constant D, where R is the rate of reproduction. So you think about how a population is going to change over time. If you have some sort of average, like if X number of children, then the addition to the population in a, say, given year, for instance, whatever unit of time you choose, will naturally be proportional to what the population is currently. And that's how we see this kind of exponential growth in population. But there's other factors to take into account. So we have, okay, so D is number of deaths per unit of time. But this population model assumes that how many specimens die per unit of time is actually independent of population currently, which would not apply to, for instance, something like disease. That there's going to be some number that describes the prevalence of a disease. What percentage of the population gets stricken with this disease? What percentage of the population dies from it? And in that case, I would have another term here, a negative term. Again, where it's some constant times the population to model death for both cases. But here we're assuming that there's a fixed rate of death. For example, if we're modeling a population of an animal species, and we want to take into account predation. If the population of predators isn't really changing, that's fixed over time, then this seems reasonable. But we have systems differential equations called predator-prey models that are population growth differential equations. One equation for the population of a predator and one for prey. And those are coupled together because those populations naturally will influence each other. For example, if and then very different dynamics can happen. If the predation rate is higher, you think that'd be a good thing for a predator, but what if it drives the population of a prey too low? Then there's no more food supply and the predator will die out. So it's an interplay between all these rates at which things happen that affects how the solution behaves. Okay. Now in this case, rate of reproduction naturally would be positive. Now, suppose I ignore the deaths per unit with this constant term d here. So in fact, I'll write down an alternative population model. Where we just have a constant times the population, where a constant k comes from, I'll write as a difference of constants. Let me make sure we're still recording. Okay, good. Right. Where in case of B would indicate a birth rate, in case of D would represent a death rate. So the net growth rate population would be the difference of these two constants. So I focus on this here. You would hope, anyway, that K would at least be positive for population growth. But some of you may have seen in whatever class differential equation exactly like this one, this kind of form, where the constant K is negative. And it's not about population growth. What might be modeling in this case when there's a negative constant there? I don't know if you can cover this anymore in calculus, but so what would be the application where instead of exponential growth, we're seeing exponential decay?
Bacteria.
What?
Bacteria.
Well, that's also a population in a way. But yeah, but if it's dying out, then yes. What would be something else? It's non-biological. Maybe we don't cover it anymore. Radioactive decay. So I don't know if any of you have been given problems like that in some other class. I don't know. I remember elsewhere I've talked about that like in Cal too, but where what the information that you're given would be like the half-life of a radioactive substance, how long it takes for the amount of substance to decay to 1/2 the original amount. And that would help you figure out what the constant K is, so that you can figure out what the amount will be at any time t. So this is relevant to, for instance, carbon dating, etc. Okay. All right. Let's see. Here's an example from a very different area. From finance. So let's suppose you make an investment. So K is how much money is invested, a fixed amount, each year. And you expect an annual rate of return. So some constant R, so you can think about it as a percentage. So if you expect a 10% rate of return, then R would be 0.1. And we'll describe S of t to be the total balance, the value of your investment. Not sure why I abruptly switched to lowercase, but okay. After time t is passed, where t is measured in years. So everything is annual. So you have to pay attention to units as you're deriving such equations. And we'll assume that S naught is the so how much does it start with before you start pouring in K dollars per year? So a differential equation that would model the value of your investment over time would be a similar form as the other ones. So however much money is in there now, you're going to have R percent piled on top of it, plus the amount K that's being funneled in each year. And then the initial condition. S of 0 is equal to S naught. Now, the solution for, I won't go through solving this equation now. Again, it'd be similar to what we saw last time. But I can tell you the solution formula for this equation would include a term like e to the RT times the initial investment. Now, I don't know if in some prior class you have our lower level math courses where you work out problems involving compounding of interest. And there could be different approaches to compounding. Is interest compounded annually, quarterly, monthly, daily, and then finally continuously? When it's continuous compounding, then we have the exponential growth. And that leads to, again, term form e to the RT in the solution. So in fact, the solution would be e to the RT times S naught, plus additional terms that take K into account. Okay. Now, I could take this equation and flip it around to describe another financial application. So what if S of t, instead of referring to the value of investment, is balance of a loan? So S naught is the amount that you were loaned originally. R would be the interest rate of the loan. So, so this term would reflect that while the loan is still not paid off, there's still some compounding of interest on the balance that remains. So, if I'm modeling loan balance, can anyone tell me what does that term represent? So if the interest is already taken into account, this additional term here, what could that be? What?
Payments.
Yeah, loan payments. But in that case, this term would be negated. Yeah, so yeah, it ought to be negative anyway. So and that's why, and this gives you an idea as to consequences of certain things that can be done. For example, if you are deferring loan payments for a period of time, then you can see from a solution formula for this that interest is still accumulating, resulting in potentially much higher balance when payments are being made again. And you can see in real dollar terms the consequences from the delay. All right, so so if we stick with the same form of the equation, K would be the amount that is being deducted from the loan balance. And then you can see what, how long would it take? Once you have a solution formula, you can figure out certain things like how long would it take for balance to go to zero for this interest rate versus this one, etc. What happens if the amount of a payment is changed? Because what you can see in certain cases that because you'd be cutting down on the exponential growth by making larger payments, sometimes a relatively small difference, the payment can make a significant difference over time in terms of paying the whole thing off. Okay, but every single equation I've written down today, all four examples, can be served by the same solution formula. These kind of first order models that are linear equations. And when we get to second order equations much later, we'll see applications of those. For example, spring mass systems modeled by a second order. Okay. Now, more concrete example now where I'll throw in some numbers. Okay. All right. So look at a mixing problem. Okay. So the idea is we have I need to make this bigger. Some kind of tank. Okay. All bottle raking is 3D. Okay. Now, initially, the tank includes 200 liters of a solution. So a dye mixed in water. Okay. The shark's not going to affect the differential equation. So, sorry, I couldn't resist. And the concentration of the dye is going to be 1 gram of dye per liter of solution. Okay, now what's coming into the tank is going to be just water, no dye involved, at the rate of 2 liters per minute. So we see the units that are being used here. Grams of dye, liters of water, time being measured in minutes. Okay, so the idea that water is going to rinse the dye out. So we have mixture that is leaving the tank also, so that's the solution with the dye being flushed out. And that's leaving the tank at the same rate. Right? So the amount of solution, regardless of the amount of dye in the tank, is 200 liters. Okay. Now, I'm going to define Q of T to be the total amount dye in the tank at time t. So that's what we're actually trying to model. We're going to come up with a differential equation that describes capital Q, how it changes over time. Now, Q of 0, so our initial condition would be the amount of dye in the tank right now before we begin flushing. And we can figure that out from the information that we have. So it is 1 gram per liter. Okay, so I should say this is the initial concentration of dye before we begin flushing. 1 gram per liter times 200 liters, the amount of solution in the tank. So just cancel the units. So 200 grams is our initial value. Okay. Now, what about the differential equation itself? So we use this starting point. dq dt is going to be flow rate in flow rate out. Now, what would the units for that be? Well, Q is in grams, and we're looking at dq dt. So this is going to be in terms of grams per minute. How many grams a minute per dye? How many grams per minute of dye are going to be entering the tank? And that'll be sign positive. Leaving the tank, that'll be sign negative. Okay. Now, in this case, we can conclude that the flow rate in is 0 because there is no dye entering the tank. It's only water. So what the interesting part of this will be how much dye is leaving the tank per unit of time. So the way we can express that, so that would be the concentration of dye times those within a solution times the amount of solution leaving. amount of solution leaving a tank is known to be 2 liters per minute. Okay. Now, what about the concentration of dye? If we assume that everything is throughout the tank, so we have uniform mixing. Then all we're doing here is we're taking the amount of dye in the tank over the amount of solution. So it's just amount over amount. So the amount of dye is going, well, that, we don't know that. We know that at the start, but this is something that changes over time. The amount of dye at any time, actually I'll write down both of these things. Amount of dye divided by amount of solution. So the amount of dye would be Q of T. So it's changing over time, and we're taking that into account. Over the total amount of solution, which is what? 200. I should mention that after listening to much loud music for longer than you guys have been alive, my hearing is awful. So, so I was when I put out a question, and I hear people talking. What I hear is like so. Speaking up is encouraged. Okay, so 200 liters total amount of solution. So now we just work all this out, and we see now Q of T is expressed in grams. And I'm putting units here because it's a nice check to make sure you're on the right track and coming up with the equation. That what we're going to wind up with is 2 over 200, or 1 over 100, so minus 0.01 times Q, and the units will be grams per minute, which is what we'd expect. So that is how much the dye is decreasing per unit of time. So it's going to be 1% of the total amount of dye still in the tank is leaving per minute. So now if I clean this up, the Q dt is minus 0.01 Q, and Q0 is 200, so that would be the initial value problem for modeling the amount of dye in the tank. So questions about how this equation came about? Now, if things are really complicated a little bit, here some convenient assumptions were made that the because the flow rate in was the same as the flow rate out, the total amount of solution in the tank was kept constant, and that's something that was taken into account down here. But suppose that was not true. Suppose the inflow and outflow rates were different. Of course, one would hope that the so what's going to happen in this case is you want 200 liters in at all times, so that's why I keep them the same. But let's suppose the you were actually not trying to end up with a solution that was free of dye. Maybe you just want to flush out a tank altogether and end up with an empty tank. You could have an outflow rate that is greater than 2 liters per minute. So then, if the inflow and outflow rates are still constant, but different. So let's suppose what if the outflow rate is equal to 3 liters per minute? Then the net flow rate is 1 liter per minute leaving. So the amount of solution is equal to, it's 200 at the start, but every minute, and t's in minutes, we're going to have 1 liter less. So if that was the case, then I'd have 200 minus t down there. So that's how the differential equation would be affected. Because the denominator is getting smaller, the concentration of dye would be slightly increasing, just because you have that certain amount of dye in less total solution. And that would also complicate matters as far as solving the equation. So then, because of a 200 minus t in the denominator, it would no longer fit the same form of equations that we've seen. We'd have to consider a different solution method. So there's wrinkles like that. When you change your assumptions, that change the form of a differential equation and ultimately how you solve it. A lot of times people make assumptions that may be oversimplifications just so they can solve the equation. Just to try to get a ballpark as to how things behave. Okay. If it was not that was entering, what if this was also had some dye in it? Then I have something down here for the flow rate of dye into the tank. Now, as it is, this equation I can just write down the solution for. And I'm pointing this out because when the equation is this simple, we just have this one term. So dq dt is a constant times q. That kind of equation comes up in various settings where it's a good idea it's just one of those things you should know, ideally. That you don't go through the laborious process of solving it like all the other techniques I'm going to teach you. You just bam, write it down. Could be, for example. So in this case, Q of t is going to be the initial value, so 200, times e to whatever constant you have here, the minus 0.01 in this case, times t. Okay, so that's the solution. And this assumption of equal inflow and outflow. Now, what we can infer from the solution is the exponential function is always strictly positive, no matter what's plugged into it. So this says that the amount of dye is never actually going to hit 0. So the amount will be extremely small after a time, so small that you could basically neglect it, and for all practical purposes, assume that it's 0. And of course, this model isn't physically perfect, but and you could use this formula to determine. Well, suppose you want to make sure that the amount of dye in the tank is under a certain amount. Like maybe you want there to be, because there's 200 grams initially, maybe you want it to be less than 1 gram, for instance. Then you can go ahead and set this equal to 1 gram, and solve that equation by taking the natural log of both sides and figure out what is the time t at which the amount will get that small. Do we have any questions about either this or homework problems? Am I making the homework too easy?
No.
Okay, so this is an interesting Goldilocks problem. So I'm not making it too easy. Apparently I'm not making it too hard either because no one's asking questions. Yes?
So you said what if the outflow rate was 3 liters per minute, amount of solution is 200 minus T?
Yeah.
Would you just plug that in exactly to the equation and solve it in that order?
Yeah, so, okay, I'll write it over here. So you have the dq dt. So all of our assumptions remaining in force, you would have, okay, so the concentration would now be, so minus out 2 over T times Q. Okay. I wasn't planning to do this. Well, actually, I wasn't planning to throw an assumption in here either, but spur of a moment. And I just hope it goes right. Solve this. Now, there's 2 solution formulas that are good to know, that they just come up often enough. So one's a special case of the other. So what I just used to solve the equation in the simplest case is that if dy dt is equal to some constant times y, then the solution is the initial value, whatever that might be, e to the kt. So wherever in your brain you like to file certain essential facts you just want to have off the top of your head, instead of having to just work through them again, you know, this is a good item to put in there. Okay. Now, if I complicate that situation a little bit, so that dy dt is not a constant times y, but it's some function of t times y, so f of t times y. Then the solution formula in that case is again the initial value times e to the integral from 0 to t of f of s ds. Okay, let me put a box around that. Okay. And you can see how the two are related, because in a special case of f of s just being a constant k, the integral would be kt. So the notice what I've done here with the integral is something that notice it's a definite integral, but I put limits in there. So if t is 0, I have the integral from 0 to 0. Well, the integral would be 0. And then e to the 0 is 1. So then I just have the initial value, as I should. But because I'm using t as a limit of the integral, I need to use a different letter in here. So that's why it's f of s ds. It's kind of a pain, but it has to be done that way. I could have written this as an indefinite integral. So indefinite integral of f of t dt, but then there's a plus c to take into account, and So this is a solution of this initial value problem, where you're given y of 0 for initial condition. Okay. Now, that second formula to solve the equation with this assumption of different inflow and outflow rates, because this is my f of t. So now my solution formula is going to be Q naught, so the initial amount, which was previously stated to be 200 grams. Sorry, I want to give myself more vertical space, so I'm just going to rewrite the same thing, but E integral from 0 to t minus 2, I'll pull the constant out, 1 over 200 minus s ds. Now, probably one was having a solution formula, I could stop there, but this is an integral that that can be worked out. What is the integral of that?
Natural log.
Yes, there's a natural log involved because we have s by itself in a denominator. Natural log of what?
200 minus s.
And there's one other thing that needs to be included in here. Sorry, what?
C.
There won't be a plus c because we'll have limits, but I do need to add limits. But there's something else?
Negative sign?
Negative sign. Why?
Because there's negative sign in front of s.
Because of a minus in front of the s. All right, so then this becomes a plus. And then we have limits, 0 and t, that have to be plugged in. Okay, so now we can go ahead and substitute in those limits, 0 and t, for s. So Q naught e to the 2 natural log of 200 minus t minus e to the 2 natural log, I don't need the absolute value in this case, of 200. And really, the amount of solution in the tank is definitely not going to be negative because all the universal law is broken. So this solution will only be valid as long as this quantity is positive. So certainly at only valid for t strictly less than 200. Okay. Now, what I'd like to do is this could be simplified using properties of logs, because I can take this 2 right here and move it over here. So I'll write the property of logs down here in case you've forgotten. So ln a to the b is equal to b natural log of a. The exponent can be moved from here to outside. Now here I'm applying in reverse. I have this situation. I want to make it an exponent. So now I have e to the natural log of 200 minus t squared minus e to the natural log 200 squared. And now that I've done that, can all of you on this side of the room see? Okay. What can I do now to simplify? Because I moved that to 2. cancel. So e to the natural log of x is just 2 natural log is something I could not perform by cancellation. By moving the 2 out of the way, now I can. So it's 200 minus t minus 200 squared. That could be simplified further just by foiling the 200 minus t, but I won't bother with that. Well, no, actually it is instructive to do that. So Q naught minus 400t plus t squared. Okay. So over time, because this dominant term here, it's negative, okay. Actually, I can simplify this a little bit. Something doesn't look right.
Shouldn't it just be 200t?
When I expand this, 200 minus t squared, I'll get 200 squared minus 2 times 200 times t plus t squared. So that's where the doubling comes from. Okay. Okay. Something looks, I can tell that something's wrong because Q naught, of course, is positive, T is positive, T minus 400 for time starting from 0 is going to be negative. The total amount in the tank should not be negative. So, certainly somewhere. Now, going back to this part of the solution formula here, before starting to simplify things, certainly natural log of 200 minus t is going to be less than log of 200, because log is an increasing function. So even here, something is amiss. This is what happens when I do things off the cuff. I totally was not planning to do this today. Okay. So 800, that would be 1 over 200 minus s times minus 1. Okay. Now, yeah, so somewhere between here and here, something went wrong. Because, like I said, e to anything is positive, no matter what this is. So we have a positive value for q at this point. Also, the integrand inside here is positive, so the exponent as a whole is negative, so it's going to be decay. So there's nothing wrong with the solution at that point. If you spot anything, but by all means, let me know. But this is going to drive me nuts. And then what will probably happen is that after you all have gone, then I'll say, oh, duh, it's this. So, stuff happens.
When did the 400T,
What?
the 400T be positive? Or,
No, because the negative here. Yeah, that's the one negative term that shows up. Okay. Yeah, so for example, if I substitute in a value, made up value of t here, the whole quantity turns out to be negative. But grand is over 200 minus s. Okay. Oh. Yeah. So what I've done here is using technology to help me out here. So I've had MATLAB evaluate this integral, just again a made up value of t, just going from 0 to 1. So then what I can do is compare this. Okay. So this agrees with this. I feel like this thing is staring me right in the face. Oh, wait. Okay. Well, the only thing that makes me feel better right now is that none of you saw it either. Okay. There's an absolute bonehead mistake. This is right. This is right. This is not. Chance to see it before I point it out. It's
that's absolute sign.
no. What was? Someone else? Okay. Fine. We all get to kick ourselves. But me hardest of all, because I shouldn't have done it. But we're teaching since 1994 that once you're up here in front of you all, the IQ just exponentially goes to zero. Okay, that's why nobody spotted it. Suppose this is subtract up here. Do everything within this one exponential. Yeah, see? And how long were we all, including me, an alleged full professor of mathematics, staring at that dang thing? So I'm glad I spotted with 4 minutes to go in class. So, okay, all of this is bogus. So, at least we can guarantee that an exponential something is going to be positive. So, we have Q naught E. All right. So, now using the laws of exponents, I have these things subtracted, but multiplied. Okay. And then I can do the same thing I did before, where I move the exponents here. Actually, here I'll move the minus also. So now I have Q naught e to the log, so that's going to cancel, and I get 200 minus t squared. And then down below, so e to the log is going to be 1 over 200 squared. Okay. So that is the dang solution. So what happens is, as time marches forward, this numerator is going to get smaller. That fraction multiplying Q naught will go towards 0. When t equals 200, the whole thing will be 0. There will be no die in the tank because there's no solution either. And the last thing I'll point out, yes, I hear you packing up. You have 2 minutes, deal with it. Is that when we assumed equal rates of inflow and outflow, this was a solution. Okay, so I'll write it down over here for the video. Versus Q naught e to the minus 0.01 t. Notice that it's decaying exponentially, but now with the unequal rates and that concentration increasing slightly as the solution has a completely different form. It's a polynomial of t rather than an exponential function of t. So that one little tweak, making the assumptions, changed everything about the solution. And even when it isn't done wrong. So, okay. Well, that was interesting. Okay, so I'll assume that everything's going up, and you really should let me know. If not here in class, then directly. So next week we'll get into chapter 2, actually solving more equations, and properly.